Thank you, Nicholas, for having me. As will everyone, that's how we say hi in my language, and it literally translates to come closer to my heart. And today I'm going to talk about the convergence of HPC and Amal workflows. So I will talk more about the challenges and give examples of how we deal with these challenges and ask a lot of questions. So if you remember Kevin from yesterday, he said he is in his early career. Well, I am earlier than Kevin. So we have a lot to learn from you. So when we talk about the convergence of HPC and AI workflows, it can be both ways, either ML on HPC or HPC on ML. So when we talk about the ML on HPC convergence, it's mostly about using machine learning components in traditional HPC workflows. It can be by using machine learning models to accelerate some components in our simulations using surrogate models, or to post-process some data to detect interesting features, or it can also be used to replace some decision-making that used to be done by humans. In the other side, the HPC on ML, it's mostly regarding using HPC infrastructures to accelerate machine learning models, or to train on very large data sets that we cannot train on single GPUs, for example. This is some challenges that we may have in this type of workflows. So on the data management aspect, we're going to deal with data. So we have to either communicate this data or store it, and we have to deal with optimizations related to that. Another challenge is related to different programming models and data models that we're gonna have to deal with in these different workflows that deal with HPC and ML at the same time. Profiling is not trivial, and if we don't understand performance, we cannot really optimize our workflows. And traditional HPC workflows are not really compatible with ML workflows or ML models. So how can we deal with that? And finally, we are dealing with a very complex software stack, either just by having the two different worlds, or when we deal with coupling of these components. So the presentation will be organized into 3 examples. I will show or talk about the problem, how we solved it, and ask a lot of questions and hopefully get some answers from you. So the first example is us trying to accelerate spatiotemporal graph neural networks. So most of, or the state of the art of these spatiotemporal graph neural networks are built for a single GPU. These are important because they deal with data that deal with both space and time. It can be used, for example, for traffic predictions. It can be used to study the spread of an epidemic and so on. So the way it works is represented here. So the data is represented as a graph, and we have like time series of these graph, like the status of this graph. And these are pre-processed before getting into the training. And this is important because I think usually the pre-processing is a little bit ignored or neglected, and we usually focus on building better models, but the pre-processing is not that good. So as an HPC person, when I got this workflow, I was like, okay, we're going to have, we have this sequential here, we have some arrows here, and we have a single GPU. If we want to deal with larger data, then these are going to be some problems, so we have to solve them. So, we're going to distribute the preprocessing pipeline. We're going to try to avoid the IOs, either by keeping the data in memory or staging it somewhere rather than going through the Power file system. And we're going to try to use multiple GPUs to accelerate these trainings. So we had to look into this pre-processing pipeline, and we found out that we couldn't, or the largest data set in traffic predictions is called PEMS. It's collected from sensors in California, all over California. And this workflow, or the pre-processing workflow, actually crashes before even we get into the training. So when we see this data growth, we're going to say, okay, we cannot do it in a single node. So, okay, we're going to distribute the data. But then at the same time, we're like, okay, let's profile a little bit what's happening in the pre-processing pipeline and see why do we have all this data growth actually. So we had to look at it, and mainly it's just like not only one model, but like two of the state-of-the-art of STGNNs are using exactly the same pre-processing pipeline. And they have mainly 3 stages. So the first stage is just like they are adding the time of the day information into the data set. The second stage and the third stage are interesting. So since we are dealing with time series, they had to apply a sliding window to that data set so that they keep the relationship or between the different points in the graph. And the way they did it is just like they will take this data and having a window which is just moving and duplicating the data again and again and again for the whole data set. And then in the stage 3, they just duplicate the same x, because for a pair x, y, where x is the input data to the model, we want to predict the next window on time. For example, I have the data for 8 to 9. I want to know how the traffic would be from 9 to 10. So this is mainly it, but the data is exactly the same, but it is duplicated. And, well, this is an issue. So instead of just distributing the pre-processing pipeline, we have introduced optimizations that are, for us in HPC, very obvious, but I don't really understand why the machine learning people didn't really apply it at the beginning. Probably because they were dealing with small data sets and just duplicating the data was not an issue, but, well, it's an issue when you deal with large data sets. So that's what we did. We introduced optimizations into the pipeline, so we reduced all these data duplications by just keeping one single copy of the data set in memory and having indices to represent this sliding window logic rather than duplicating the data. And we have used Dask distributed, which is a very interesting workflow management system, Pythonic one, to distribute the pre-processing pipeline and couple it in situ with the training, which will avoid us going through the parallel file system to read back the data for training. And these are some numbers of the scalability. So the first thing to note is that for the best of our knowledge, no one had trained spatiotemporal graph neural networks on the PEMS dataset, which is the largest that we have. So we were able to, first of all, to make it work. Just the first solution here is just by distributing the data, distributing the pipeline. The second thing is that we were able to have a perfect scaling when we introduced our memory optimizations, which is excellent. And so we had actually to know more about the workflow. So here, since the largest data set fit with our optimizations fit in a single node memory, we kept it duplicated in all the nodes. So we avoided all the communications. That's why we have this perfect scaling. And then if we have larger than that, it's obviously better to have also the distributed version integrated. And thus we can see like we have here some overhead when we have the communications. But both solutions are there and people can use them. So, okay, this is good. We had this one example. We applied our optimizations or what we learned from HPC into this machine learning workflow. But then how can we deal with other workflows? Is it always the case or not? And here I have some questions. Feel free to answer them if you can. So this data keeps growing in every domain. So what are your thoughts on data processing and pre-processing workflows from different perspectives? So the first one is the efforts. Do we have these pre-processing libraries for AI? Don't we have them? Why don't we have them? Is it very specific to every model? Can we factorize that into categories of models? Or I don't know how to deal with that. And the efficiency is, are we going to have these libraries at some point, or it's very specific? How can we deal with that? And finally, the relevance of the data itself, because with the current scale, we cannot have always the human in the loop to validate the data, to filter and say, this is good data, this is not good data. So would AI agents be able to judge whether data is relevant enough for a given topic? And how can we do that? If so, are the current inference mechanisms ready for the large-scale data that we are dealing with? If not, how can we improve that? So with that, I will go to the second example. So part of the first example was about profiling and trying to understand the workflow, its performance, and the memory usage, and so on, which is not always that easy. So in this example, I will talk about the performance characterization of task-based workflows applied to Dask. And here we touch to the difference to the point where we have different programming and data models, and HPC profilers are not enough now to study this kind of workflows.
Yeah.
So I start with a simple, a small comparison between MPI and task-based programming models, and I focus again in Dask, and show how these fundamental differences can be an issue. So, for example, how we define data. It can be a simple question, but it's not that simple than that. So in message passing, well, we can say that, or in applications distributed using MPI, we can say that a data can be defined as a value of a buffer at a given timestamp, which is immutable data and which is local to each process. When I say that this is the memory usage in this process, I understand where this memory comes from because I know the code. But when it comes to task-based programming models, well, a data can be defined as an input or an output of a given task. This data is immutable, and the same data can live in different processes. So when I say that this worker or this process has this memory usage, I have no idea where it comes from, which task is it coming from. The same thing for the communication and also the scheduling. So for MPI, we already know in advance the communications, where they happen, when they happen, and which data we are communicating, and so on. For task-based programming models, usually the scheduler is responsible for getting the data when it is needed by a task, and we do not really have more than that information. So if we say that a process is communicating, okay, which task triggered this communication? So we need to understand that to optimize our tasks and make them better. So the traditional performance tools are not tailored to capture task-level data and then correlate this task-level data with low-level data so that we understand which task is being an issue.
Yeah.
So, and here we have an example. So we have three main workflows: an image processing workflow, a ResNet fine-tuning, and an XGBoost regression model. So the goal was just to study that. So traditionally in HPC, if we have something like this, where we say, hey, we have this time spent in IOs, this time spent in communications, this time spent in computation, it's usually very enough to say that this is enough to understand my workflow and the performance, and I know what I can optimize or not. But actually, for such workflows, this doesn't say anything. And I can't really optimize something I don't understand. So we had to go further, or to get more data, to collect more data to understand where the performance issues are coming from. And in here, I will focus on the IOs and how we use Darshan to understand the IOs. So Darshan is used in the HPC community. It gives interesting insights into your applications I/O, when they happen, what type of I/O, the size of the I/Os, and so on. But when we tried to use it with these task-based models, it was not enough, and it wasn't that relevant to us. So the main reason is shown here. So in traditional HPC workflows, again, when I associate one Darshan log with a process, I know already which IOs are done by this process, and it's enough to say that, okay, let's optimize or not this part of the IOs of our application. But in task model or task-based models here applied to Dask, we're going to have, okay, one single node associated with one process, which is called the worker in Dask. But then we're going to have a lot of tasks that are run there, and we do not really know which tasks are running in that process. So we cannot really say that these IOs are done by this process at this given time. So we had to adapt Darshan to collect more data so that we are able to correlate the task level data with the low level data. So we have this system where we added plugins to the Dask workers to collect task level data. And then we have added also some other data to Darshan, such as the timestamp and the thread ID, so that we will be able to correlate, at least afterwards, not in situ, the performance data of our workflow. So mainly, mainly we had to collect these two things, and then we had to deal with the differences in the file formats of the different outputs, and then we had to do some pre-processing to say, okay, this task is going from this moment to this moment. All the IOs done by this thread between these two timestamps are the IOs done by this task, and then we can study further. But it wasn't that easy to deal with this type of workflows or to understand this type of workflows. So at the end of the day, we could have an interesting study, and okay, this looks complex, but at least it gives more data about the workflow itself. I can say that, well, this type of tasks, which is reading the data mainly, and it happens in the 500 seconds of my workflow, are taking the most of the time, and they are related to the IO operations done there. But there is also an issue here because the size of the task is very, very large compared to the size of the task recommended by Dask. So all of that has been said, we can find the correlation between these reading or IO tasks and some warnings from Dask saying that the event loop is not responsive. So these workers are doing some heavy tasks and they are not responding to the scheduler, which may cause an issue. So now we can understand further, but we had to collect more data and adapt more tools to get that type of insight to these workflows. So, okay, this has been done again for this use case, but it's not the only one, and Darshan is just an example, but we have other tools. So are we going to adapt all the tools? How interoperable are the other tools or the performance and the profilers? How we can how we can use them with other tools, and how to make their outputs fairly compatible. When should we stop adapting these tools and probably think about new tools with low overhead? Because yes, we have tools in machine learning, but they add like a lot of overhead, and we don't want that because HPC performance. And well, or are we just gonna be lazy and use all these tools and create just machine learning agents to do the correlation and the performance study on our behalf? Can be a solution too. Now I will move to our last example, and it's a bit related to the fact that dealing with different programming models can be an issue. And the workflow here is an advanced photon source tomographic reconstruction pipeline. So mainly we have an instrument generating these projections, then these projections are passed through another preprocessing pipeline, and then we do some reconstruction. And we want to couple that with some machine learning models to be able to detect some interesting features at the early stages of the reconstruction rather than waiting for all the projections to arrive. So we have some code already there, which is coupled using 0MQ, but the workflow is synchronous, so every single component needs to be there to start the others. It's not resilient, so if my reconstruction fails, then we're going to lose all the data, and we don't want that. And they are all tightly coupled, so if I change something about the preprocessing pipeline, I need to change the coupling with the other pipelines, and we don't really want that. So our way to deal with that, we have coupled the whole workflow using an HPC Kafka inspired streaming system. So mainly, we have another component. We stage the data to make it more resilient. And we organize our data into topics, and every topic has multiple partitions. And we can plug more components to the system. So now it's not just about the data acquisition component connected to the distributor component that was the case for the previous workflow, but now I can have other components connecting to the same topic and getting the data, and it applies to all the other components. So it's not a fixed architecture, but we can add more components. It is more resilient because even if one of them fails, I still have the data in our other servers. It is asynchronous. I don't need the data acquisition component to run with my other components. And we have also an interesting data intermediate data representation where we keep the data, but also metadata related to it, so that even if we change the way we adapt the data or the way we process the data, we still have a lot of information so that we know how to use it. So it is a way to couple this workflow. We could go in situ, just like moving the data from the memory of the single component, from the memory of the first component to the memory of the second component. It can be in the same node, it can be in different nodes, and so on. So I will go fast in this and just ask the questions related to this topic. So code coupling can be very challenging in heterogeneous workflows when we deal with different languages, different programming and data models. So why don't we have adapted tools yet for for ML on HPC workflows? Is it too early? Is it, I don't know. I mean, why don't we have that yet? So another question is, how can we enhance the productivity in developing this type of workflows? Because it's really difficult. You have to understand all the data model. You have to understand all the programming models if they are different. And it takes time. And if someone just tightly couple or inline his code in the larger code, it's going to be just more complex and very hard to maintain, and no one would use it later. So how can we improve that? And then some ML again. If LLMs will be used to couple codes, for example, HPC and ML or other type of workflows, how would the data semantics rigorously managed? Should be there like a list of rules that the LLM should verify or check before proposing the coupling, or how would that be? And with that, I have one left slide. So in this talk, I kept complaining about a lot of challenges mainly. So I talked about the ML on HPC that introduces a lot of complexities and challenges, either in data management or the fact that we deal with different programming and data models and a lot of software stack that we have to deal with to couple these codes. Another point was the fact that we cannot optimize what we cannot measure, and for such type of workflows, profiling is not trivial. It's not easy to do. So I gave the example of Darshan as a very known IO profiler tool that cannot work for such workflows. And finally, I think we don't apply the lessons learned from HPC and ML workflows yet. So is it a communication issue or something? I don't really get it. Yeah, thank you. That's it for me.